to look at two topics in this lesson. One is electron affinity and the other is metallic character. So let's begin with the electron affinity. Electron affinity, that abbreviated E sub A, is kinda the opposite of ionization energy. So instead of removing an electron, we're going to take an atom and have it accept an electron. So it's going to be an energy change, and when you put that electron on. So we have to be kind of specific. The atom needs to be a gaseous atom, okay? And it's going to be, and we're going to be forming an anion, okay? So we have a gaseous atom. We're going to put an electron on. The energy will change as that electron is taken on, and that's what we call electron affinity. So here is a representation of that process. We've got a gaseous atom. We're taking on an electron. When you take on an electron, you become negatively charged. So we see that negative charge. And the delta H associated with that process we would call, or the energy change associated with that process we call electron affinity. Now, think about having an affinity for something. If I said I have an affinity for gold and diamonds, that means I really like it, okay? I really want those gold and diamonds. That's what an affinity for something means. If something has an electron affinity, that means it wants an electron. And if we think about the periodic table, of all the elements on the periodic table, who wants an electron worse than anybody else? That would be our halogens. They are one away from having a noble gas configuration, so they really want to take on those electrons. Those halogens have a high, we call it a high electron affinity, because they really want the electron. Now, how does that play out with numbers? It wants that electron so badly that it is willing to pay for it. So it gives off energy when it takes that electron on. If you think about the energy as the payment method, okay? I'll give you energy when I get that electron. If something does not want the electron, you have to force it on. You say, you will take this electron, and you have to supply it with energy to push it onto that atom. That would be something that does not want that electron. Now, it's going to be surprising with the values of these, because we can take some metals and they kind of have pretty decent electron affinity because they can fill up a subshell of some sort. So they'll take on electrons. But the value, what I need to make sure you understand, it can be positive or it can be negative. Unlike ionization energy, which it always requires energy to pull off an electron. When you take an atom and it takes on an electron, it's either going to really want it and accept it and give you energy, or you got to force it on, you got to give it energy in order to make it stick. All right? So a large negative number is translated as something as having as an atom that really wants an electron. And a lot of times we'll say it has a high electron affinity, even though it's a really negative number, okay? It has a great affinity for that electron. The language is a little confusing, and actually some textbooks that I have taught from will change the sign and say electron affinity is the opposite of the value of the energy. That way you can say it has a high electron affinity and give it a positive number. But our book that we're using right now doesn't do that sign swap. But you need to realize that things that have a negative electron affinity want that electron and are giving you energy for it. It is an exothermic process. All right. The trend is ugly. I mean, it really isn't very much of a trend, but the tendency is, as you go from the metals over towards the nonmetals, to have an increasing desire to take on an electron, with the halogens being the most negative of the electron affinities. So that we can say with certainty. Halogens have the highest electron affinity of all the elements. Now the trend kind of goes like this. It is up and down all over the place, with the halogens ending up really high. And there's some nonmetals in which it's zero. Essentially, it doesn't want that electron one way or the other. So it's not much of a trend. Generally speaking, for our metals on the left side of the periodic table, they tend to have, less electron affinity than those that are nonmetals. So that shouldn't surprise us at all. We would expect the nonmetals to want to take on electrons. We would expect the metals not to want to take on electrons because they prefer to lose electrons in order to get their noble gas configuration. Look at these numbers. Let's go over here and look at them. all over the place. But we can say with certainty that the halogens have the most negative of the electron affinities. You'll notice that there are no positive numbers given. It is hard to determine how much you have to force an electron to be taken on by an atom. But our oxygen group here, they tend to want to take on an electron. Their nonmetals tend to want to do that. Nitrogen is very strange. It's actually got a positive electron affinity. I want to just talk to you about why that would be. To look at the strangeness of some numbers, what we would need to do is look at its electron configuration. So nitrogen is helium, 2s2, 2p3, 1, 2, 3, and what does that look like? It looks like this. Boom, we have half-filled that subshell. There is great stability in having a half-filled subshell. So nitrogen is pretty unexcited about taking on an electron for that reason. So when it try to take one in, it would have to put it into some place, and then it wouldn't be as stable as if it were not there. So nitrogen is a little bit unique in that regard. If we come over here to lithium, we might say, well, there's a metal that would really like to lose an electron, and it has a negative electron affinity. It would be willing to pay you for it. But if you looked at the electron configuration of it, which is 2s1, sorry, 2s1. If it took on an electron, it would fill up that subshell, and that's not a bad thing. So it's, you can actually make it take it on. It doesn't tend to do that, though. It tends to lose an electron because that's what our metals do. Okay? So, trend. Generally speaking, it increases as we go to the right, but as it increases steadily, no. Negative 43 jumps up or down to negative 134, back up to negative 172, so it's all over the place. General trend, increasing, more negative as you go to the right. Electron affinity is increasing as you go to the right. I shouldn't go to argon because they definitely don't want electrons. Going up and down a family, do we see much of a trend? No, okay, can't really say much of a trend as we go up and down the family. But you ought to know the definition of those, know the definition of ionization energy, know that the halogens want them the most, and that'll be good. All right, the next thing we need to look at is metallic character. Metallic character is a measure, and it's not a numerical measure, it's kind of a comparison measure of how much metallic property an element has. Well, we know that our nonmetals sit over here on the right-hand side. They don't have much metallic character. And our metals are over here on the left-hand side. We have the metalloids, which are kind of bridging the gap. But even on the metal side, if we compare one metal to another metal, some metals have a higher metallic character than others. What does that mean? It has a stronger desire, I don't know if desire is a good word, it's a terrible word, to lose electrons. Okay? It's easier for them to remove electrons. That's really what we're saying. The easier it is for that electron to be removed, the more metallic it is going to be. And we see this trend of metallic character just by the layout of the periodic table. We know that our nonmetals are in the top right, our metals are at the bottom left, and with that trend, we could compare any two elements and say this element behaves with higher metallic properties than this one does, and that means it's easier for it to lose an electron and become a cation. Last thing I want to leave you with is once you have an understanding of ionization energy, let me write that down. Once you have an understanding of ionization energy and its trends, who wants to have an electron removed and which one is easier, and you have an understanding of electron affinity and its general trend of the metals not wanting to lose their electrons, the metals not wanting to gain an electron, but the nonmetals do want to, and we have trends for that. Once we have trends up and down a family of these energies, especially the ionization energy, then we can understand the chemical behaviors and start making judgments about which elements are more reactive based upon the size of these energies? What does their reactivity do up and down a group based upon these? So what I want to leave you with is I want you to look at these three groups. Your alkali metals, that's the far left group, the halogens, which is right before the noble gases, and the noble gases. And I want you to read and be responsible for why are these reactive the way they are, or not reactive, as the case may be for the noble gases. What can we say about their reactivity as we go down the group or up the group based upon our energy arguments? You read about that, and that's the last thing that we're going to cover in this chapter.